All right. This is a lecture, the first lecture in the chapter in the section on electrons. So we will talk about electron transport. I will draw from Abrikosov, Mott, and Kamran Benya's books, and some recent developments, of course. So let's take a look at the microscopic transport mechanisms for electrons. The first and most classical way is, of course, the Boltzmann transport equation, which is based on on the concept of mean-free paths. We saw that in the introductory chapters. Classic diffusive transport happens when the mean-free path is smaller than the sample dimensions. There are then two classes. We, in the introduction, treated the Fermi liquid, in which the electrons is essentially an ideal gas. And that is then corrected by the band structure, which reflects the periodic potential of the atoms that influences the electron motion. This is all what you're most familiar with. There are other regimes. Hopping and tunneling can occur when the mean-free path becomes short compared to the distance between defects or traps, or, for example, when there are walls, such as potential barriers in the system. And then there is a ballistic regime where the electron mean-free path, in fact, is larger than the sample size, and then we are going to have transport that follows essentially Ray equations. We'll establish the criteria for diffusive transport in a minute. To this, there are then corrections. The first corrections are the quantization effects. That you can have size quantization, where the particle wave function is affected by the finite size of the system. You can have weak localization, where the electron interferes with impurities, and the wave function then becomes split by the impurities and have interfering, constructive or destructive interfering effects. And then there are Landau levels, where the electron wave function is influenced by the external magnetic field and in fact becomes quantized. That's one set of corrections. Sometimes they're dominant, they're not really corrections. Another set of phenomena that are going beyond the diffusive transport are collective phenomena. Typically, we will have then electron interactions become stronger, for example, than electron interactions with the potential wells of the atoms. That becomes then the case for heavy fermion systems and systems with valence fluctuations. Typically, this happens in rare earth metal, in solids that contain rare earth elements. There are others, of course. You can have electron-phonon interactions that become dominant. For example, an electron-phonon-electron interaction, electron-electron Cooper pair coupled by a phonon, will lead to superconductivity. We're actually, in fact, not going to treat superconductivity here. And another classic one is that an electron and a phonon, or an electron and a local distortion of the lattice, can become intimately coupled and become one quasi-particle, electron plus phonon. That's a polaron. There are further corrections that are possible. These are resonances between the electron that does the charge and something in the crystal. These interactions can be spin-based, can be magnetic-based. That would be a Kondo effect, either with dilute impurities in the solid or even with majority elements, manganese tellurite. The manganese is 50% of the solid, and there can be Kondo systems in there. They can have resonances with charged impurities. This is typically the virtual bound state or the resonant levels in semiconductors. There can be resonances with phonons, resonant electron-phonon interactions. For example, the Nielsen-Taylor effect, which is really some sort of thing that looks very much like a virtual bound state for charge. But in fact, the effect of the Nielsen-Taylor effect looks much more like those of phonon drag. And so then we have the fifth, this should have been 5, advective transport. This we talked about before. This is the drag where the force is exerted on one particle, phonon for example, and then gets transmitted to another particle like the electron. All right, so let's go over these systematically. Now, I know that the physicists and material scientists amongst you have had their Fermi liquid and their band structures, but the mechanical engineers didn't, and so I will give a very quick review of classic band structures, and I hope not to bore everyone with this. If you want, you can skip to the slides that are dealing then a little further. But let's just go down for the classic picture for the Fermi liquid and the band structure. So first, the Fermi liquid. It's an ensemble of electrons near the Fermi surface of a metal or a degenerately doped semiconductor, and these electrons behave like free electrons. Of course, the effect of the periodic potential of the atoms on these free electrons is to correct their mass. So we really use the effective mass as a single parameter that reflects the fact that the electrons are not quite free. So it's not the free electron mass of 9.1 10 minus 31 kilogram, but a corrected mass, effective mass. Nevertheless, the equations of motions are those of the free electron with just a parameterization. We assume electrons don't interact, so we're going to ignore the Nielsen-Taylor effects and the Kondo effects and the collective phenomena and heavy fermions. And the dispersion for the free electron, of course, is going to be classical mechanics first. It can be corrected for relativistic effects and Dirac-Hamiltonian, but let's just take the classic mechanics. E is mv squared, kinetic energy is mv squared over 2. In other words, it's p squared over 2m. And because in quantum mechanics, E becomes h by omega and p becomes h by k, E becomes h by squared, k squared over 2m. That p becomes k squared. The velocity then is dE dk divided by h bar, which actually we can trace back to these equations of motion. Now, typically, most solids that we treat with have anisotropy of some kind. And so the simplest model that represents most classic semiconductors, silicon, germanium, indium antimonide, lead telluride, gallium arsenide, I'm going to use this ellipsoidal Fermi surface for our solids. So that means that if you have Kx, Ky, and Kz in your system, you can have different dispersions along X, Y, or Z. Basically, you have different shapes of this parabola, which means that you really have different masses. And then you write the total energy as Kx squared, Ky squared, Kz squared with different values of masses. And that also means, of course, that the dispersion gives rise to different group velocities, because the derivatives vis-a-vis Kx, Ky, and Kz, if E is different, it contains these different masses. Now, the comfortable way to treat this is to define the effective mass tensor and to define your energy as h bar squared over 2, and then the K vector mass tensor K vector transpose. That just gives the previous law, but in a little algebraic form. Velocity is then the gradient of the energy vis-a-vis one of these Ks, so it's a vector. And your Fermi surfaces look something like this. They have these ellipsoids which are not necessarily aligned with the principal axis of the principal crystallographic axis of the system. The ellipsoids have their own principal axis, and you can get them into a crystallographic system by just making a matrix rotation. So that's things that you have seen in algebra, and we won't go into detail. Now, we then apply the Boltzmann equation to this. So each particle has a position, x, y, z, and has a velocity vx, vy, vz. You assume that these velocities are distributed randomly and uniformly. You assume that the number of velocity vectors equals the number of particles, n. And then you have a real space volume, which is the integral of kx, dx, dy, and dz. But you have a phase space in which we're going to be working, which is a space of the velocities, or the space of the momentum kx, ky, kz. Since this is just as much a characteristic of your electron as its actual physical position in the system, that means you also have the phase space, which is the integral over kx, ky, and kz of whatever property it is that we're going to be discussing. So that's phase space. And you then have the classic theorems for statistical mechanics. So if you have a particle, you integrate dx, dy, dz. But if you have a phase space, you typically make that integral. You can make it in spherical coordinates like we do here. So we have to integrate dkx, dky, dkz, or we integrate d, and then we have an elevation angle, we have an azimuthal angle, and we have a radius, and it's the same principle. So let's go quickly over the concept of band structure. Let's assume now that we have atoms at these positions here in real space. This is the potential then that some electron that's going to go over this will see. Well, so that potential has these parabolic-like values that correspond to the charge on the core electrons and on the nucleus of the atoms at these locations, which will interact coulombically with the charge on the electron that flies over it. Now you can quickly see that these potentials are periodic with the periodicity of the lattice, A. You will then also see that the electron wave function, the wave function of the electron that moves over that, has to have a periodicity in frequency and in real space, but the periodicity in real space will be a function of A, and therefore you need to define the wave vector K only over the unit of A, because you have the periodic Bragg condition that EIKA is the same as EIKA plus capital K. And so this having to be periodic, that means that you have a periodicity in lowercase k that is going to go over 2 pi over A, where A is a periodicity in real space. That is also very classical. I'm sure you have seen this before. So we need to define the electron dispersion here. The bound electron dispersion is only weakly perturbed. We will assume that. So it's a nearly free electron. This periodic potential is a small correction on the motion of the electron. When that breakdowns, that's where you get into much more complicated things. But we will assume that here. So we assume that the wave function, that the kinetic energy is the same form as we had here, but we impose then this Bragg condition. So if this is the wave function with k, the real space, this wave function has to repeat itself at the next period, capital K being 2 pi over A. And that means that since these functions are identical, you really need to define it over only one space here, which is from 0 to 1/2 of capital K, but the periodicity in the reciprocal lattice. Okay, so I can take this last few graph, but now we have a theorem about degeneracy at this point. So in fact, this is not allowed, and because of that, the bands split. So this, the E of K has to open a little gap at this periodic point here, and then you end up with a band that looks like this in the first zone, and that looks like that in the second Brillouin zone, in the second periodic part of the Brillouin zone. Okay, so 1, repeat, 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 etc. So this is what the bands then look in K space if you go beyond the first zone, the second zone, third zone. And what you do is you fold them onto each other. That's just a representation. That doesn't represent reality. And so the bands then look like this because we can project everything in a single Brillouin zone, 1/2 of 2 pi over A, so pi over A, which is the first zone here. And so this is the band that looks like that. So you have these little gaps at the edges, but you can also have this gap here that opens in the middle. That's this one projected to the first Brillouin zone. Okay, so hence this Brillouin zone scheme and the spaghetti diagram. Oh, I pushed the wrong button. Okay, and so then you can take calculated Brillouin zone scheme for, I forgot what this solid is, so, yeah, whatever it is. So this is the zone center. This is the zone edge along one crystallographic direction. This is 100, I think, I'm not quite sure. This is the zone edge along another one. This is 111. So we have these zone edges here, and we have the most fundamental level here, the next one is here, the next one is here, at the gamma point. All right. So you have these levels. These are levels that are accessible to all electrons in the system. Now, you have to then fill these levels with the number of electrons that you have available in your solid. So let's start filling these levels. Let's imagine that we are looking at, say, solid neon. Your neon atom has 1s electrons, and that will go here. Your neon atom has two 1s electrons, and so it will fill these here, I'm sorry. Then we have two 2s electrons. So the 2s electrons will fill this band here. So far, nothing moves. Then we have two p electrons. It will fill the next band. And then we have 14 2p electrons per atom, but they won't fit here. They will end up filling it to a certain energy that's then going to become the electrochemical potential. So let's see, it has 14 2p electrons, which actually fills this band completely. And then it has no electrons to fill the next band. So in fact, the electrochemical potential will fall somewhere here in this band gap. All the lower levels are full. None of the higher levels have any electrons, so this thing then becomes an insulator. Now, if we have metals, let's take a look at lithium, which in fact is pretty much like neon. It has two 1s electrons, they go here. And then it has 2s electrons. Yeah, I understand lithium. And then it has one 2s electron. So it fills the next band only halfway. So now the electrochemical potential comes here. And these electrons here are free to move. And so this now becomes a metal, because this band is not filled. All right, so that means if I were to take, let me take a look back. Let me now look at this band. The energy versus momentum of this band is kx, ky, kz. It's actually isotropic, and it's here. But you have electron levels only up to here. You don't have enough electrons because you only have one 2s electron. You don't have electrons to fill it up here. So that sets your electrochemical potential. And if I were to trace out the shape of the surface here in momentum space kx and ky, kz, I would have, for the value of energy that equals the electrochemical potential, I would have a sphere, because it's the same dispersion in kx, ky, and kz in lithium. So the Fermi surface of lithium is a sphere in this very simple approximation. Actually, it isn't, but it is for potassium and it is for sodium. Here, the Brillouin zone is a little bit too small, so it's not quite a sphere. It has a sphere, but it touches the next sphere, the next Brillouin zone, right at this point a little bit, so then it actually does have to open a little gap. Okay, so here then are the Fermi surfaces of all the elemental metals. So we discussed lithium, and it's not quite a sphere, it's a sphere with this little thing that touches the next zone over. But sodium is a nice sphere, potassium is a nice sphere, rubidium is a nice sphere, and cesium has a problem. Cesium, in fact, also has its 2, 3, 4, 5, it's 6s electrons band, half full. But cesium is a much larger ion than, say, lithium, and therefore the Brillouin zone is much smaller, and you have to accommodate the same number of electrons, so you can barely do that, and that's why then cesium touches the next Brillouin zone. In the cesium Fermi surfaces touches the Fermi surface in the next Brillouin zone at these little holes here that you see, which are little necks in the bath structure. That's very pronounced in copper, or silver, or gold. So these are signatures of the S bands that are unfilled. Here you will then have, this is beryllium, you will have S electrons, but you will see the appearance of p electrons in the unfilled bands. So a nice example is magnesium, where you have a little, it's like an egg on a plate. The yolk is S electrons, but you see the appearance of p electrons at the edges that are free. They're not bound. And these metals are hexagonal, so that surface is a little bit more complicated here. If you go, on the other hand, to calcium, which goes back to cubic, essentially you have the two p electrons behave, but you have five, so the two 5p electrons here, 1, 2, 3, 4. The two 4p electrons here behave very much like the 4p electron here, but there's more of them, so now all these surfaces touch each other. That is because this is cubic, so it looks like calcium looks like potassium, but it's blown up. Whereas magnesium, being hexagonal, looks actually quite different. Magnesium, zinc, and cadmium have pretty much the same structure. Things become far more complicated when you have d electrons. Scandium looks like this, so you have S and d electrons, and here you have S and p and d electrons. Now, when you have the magnetic, like iron, cobalt, and nickel, they will have a spin-up structure and a spin-down structure. That's not actually shown here. All right. They only treat the metals, so you don't have the really interesting ones like lead. Lead is here, bismuth. Here, I didn't get it on the screen. If you go to the website, you won't find them all. They don't treat the semiconductors, so you don't have any here. Okay. Now let's take a look at semiconductors. So in semiconductors, the arch example cartoon is some sort of two-dimensional silicon. Silicon has 4 p electrons. It has its S electrons on the core. It has 4 p electrons on the outer shell. But you can see that they can become common for every pair of silicon atom, one by one. So they are pairing up silicon to silicon. And so in a sense, these are not free electrons at all. They're bound. Okay, so we can do the count. 1s, we have 2. 2s, we have 2. 2p, we have 14 in the core. 3s, we have 2, and 3p, we have 2. It's not p electrons, it's both s and p's. So we have 4 electrons available for bonding. But since you have 4 neighbors, all the bonds are satisfied, and the electrons fill a valence band. None of these electrons become free electrons. However, the distance between the top of the valence band, which is full, and the bottom of the conduction band, which is empty, is 1.1 eV. Which means when Kt at room temperature is 1/40th of that, it means that you can have electrons that through thermal agitation can jump this gap. Not many, some sort of an exponential of -40, but still, that could happen. If, on the other hand, you go to a higher temperature, like say 3000 Kelvin, I'm making that up, this stuff is liquid by then, you would have 0.25 eV, and so now E minus 4 would be the probability that you have this transition, so you would have quite a few carriers, in fact. All right, so in principle, at room temperature, almost no conduction electrons get excited, but you have then gaps here between conduction band and valence band that depend on the material. So in silicon, we have a 1.1 gap, almost nothing gets excited. In germanium, on the other hand, we have 0.67, so we have a much higher probability to have some thermal excited carriers. If we go to indium antimonite, we have 0.16. In fact, we have a very high probability, e to the power, let's say, 0.025, 0.03, so down to the power -4, so that they get excited, and that's quite a lot. Since on top of that, the electrons in the conduction band of indium antimonite are very, very mobile, the thermally excited electrons will really dominate transport much more than the localized heavy holes. Okay, same for the narrow gap semiconductors like lead telluride. This mercury telluride is not on here, but it is a similar thing. Now here is a very, very useful paper by Christian de Bolle in Nature 423, which gives you these energy gaps of all these semiconductors, classic semiconductors, but vis-a-vis a reference level that is the vacuum level. So this is the energy of the electron, the free electron in vacuum. This is the energy of an electron you would have if you had an electron at the bottom of the conduction band in silicon, or aluminum nitride, or indium nitride, or indium arsenide, or indium antimonide. And that means that if you glue two of these semiconductors to one another, you will actually have bands that align with these band offsets, offsets between the band gaps, between the band edges of conduction band, or offsets between the band edges of valence band, and all of this is calculated. Very useful reference. Now, as you also know, you can dope semiconductors. That is to say, if you replace one silicon here by one arsenic, which has two s electrons and 3 p electrons, you have one extra electron that is not taken by the binding to the neighboring silicons. That extra electron can just float freely through the lattice. Floating freely through lattice means it goes into the conduction band. If, on the other hand, you put in a piece of gallium, which has 2 s electrons, but only 1 p electron on its outer shell, it's missing 1 electron, which means that a neighboring electron from a neighboring silicon can fill that hole, and then you can have transport of charge by the transport of the absence of an electron. What that means is you have, in fact, a free position open in your valence band. That is what a hole is. And that means that your electrochemical potential necessarily goes down and comes closer to the valence band edge, or even inside the valence band. If it's inside the valence band, they're called degenerately doped, and that means this behaves like a metal. If it's inside the conduction band, it's also degenerately doped, and it behaves like a metal. Okay, so the Fermi surfaces of these classic semiconductors are very typically, so if they're doped now, n-type doped silicon, they have Fermi surfaces just like metals, and they are little ellipsoids that, in the case of silicon, are along the 111 axis, the 100 axis. If you are in germanium, they're also little ellipsoids, and they're along the 111 axis. This is for n-type material. P-type material in silicon and germanium, they have a valence band that remains at the center. Well, they have a light valence band, a heavy valence band. And the heavy valence band remains at the center. Okay, one word of caution, that's always a mixture between the concept of electrochemical potential and the concept of Fermi energy. In the case of a metal, we have no problem, because you have this electrochemical potential is defined, say, vis-a-vis the level of vacuum, so it falls in a band, and it's a well-known quantity. This distance, the red length of the red arrow, is called the work function. Now, if you have a semiconductor where your electrochemical potential can fall somewhere in the gap, that's actually not rigorously defined because it moves if you remove just 1 electron. So we have to define something, and we define it as the average of the value needed to add or to remove 1 electron. So there we go. Basically, in an ideal intrinsic semiconductor at 0 Kelvin, if you have as many states available in the conduction band as in the valence band, this will fall right in the middle of the band gap. Of course, the moment you add temperature, things change, because you can have, if you have a little difference between the density in the conduction band and the valence band, you can transfer thermally electrons from the valence band to the conduction band, but it will affect the potential in the valence band differently than the way it affects the conduction band. And so at the end of the day, you can have Fermi levels that are depending on temperature. That's what we call the Fermi level. That's what we call the electrochemical. We can have electrochemical potentials that depend on temperature. The Fermi level is the electrochemical potential defined at T equals 0. So that is uniquely defined. This varies with temperature. Electrochemical potential varies with temperature. Okay. So again, this is a very elegant picture. We will use it extensively, but it is the result of a number of very strong hypotheses. Instead, we assume that the potentials exerted by the atoms are weak, but they can be strong. Bands then become very flat, little energy change per momentum change. That's the bandwidth becomes narrow. We can have impurities that have much deeper potentials than the atoms of the host atoms. Electrons can get trapped there. We can have potentials that are not periodic, example in a liquid. Then you have no Bragg condition. You cannot define K-space within pi over A, because A is not well defined. It varies from location to location in your solid. So you cannot really write the band structure. You still have, though, the available states, the density of available states. And then you can have your electron wave functions affected by things other than the electrostatic potential, extra magnetic field, spin orbit interactions, finite size effects, interferences around impurities, and strong electron interactions with electrons, with impurities, magnetic impurities, or phonons. Okay, so we need to set the limits where this simple band structure picture is applicable. Well, in the simple band structure picture, we are going to be able to use the length, the mean free path. And we are going to have to compare this mean free path, if we assume it exists, vis-a-vis the other classic length scales that matter to the electrons. So the first thing that we need to compare it to is electron wavelength, or the de Broglie wavelength. This I can't pronounce in English, the man is French, and it's read de Broglie. Okay, so let's call this lambda. And if we take this in the very simple picture that I showed you before, the K vector at the Fermi level, or at the electrochemical potential, is just 1 over 2 pi lambda. So this is related, directly related to K. So in a metal then, because the density of free carriers is related to Kf cube, of course this is related to lambda cube directly as well. So that's one first thing. Anything that has to do then with interferences will have to deal with this wavelength. The second problem, quantity we use, is the electron mean free path. We define this, it's average distance between collisions, and it's sometimes necessary to make the difference between elastic and inelastic collisions. So let's just say we don't make that difference yet, but don't be surprised if we later do. Very often, if you have a classic diffusive transport, so if this concept is useful, then you can relate this mean free path directly to a mobility measurement, which is the, when you work this all out, it's the ratio of the mean free path over Kf. So in other words, it's a product of mean free path times lambda. Something else that matters is the effective Bohr radius. So the Bohr radius is, in fact, it's something related to the wavelength, of course. It's the spatial extent of the wavelength, but it takes into account Coulombic interactions between electrons that will be screened. So we'll get to that in a minute. So it does measure the spatial extent of the wavelength of the wave function, and it's distinct from the wavelength itself. And then something that's really important, correlated to that, is the screening length, which is purely Coulombic potential screening, Thomas-Fermi screening in metals. It's also called the bi-screening in semiconductor, which is just a different relationship here, but it's the same physical concept. And we will see that this Thomas-Fermi screening length is related to this Bohr radius and lambda, or Kf. Okay, so let's define them a little bit better. So The Bohr radius in atomic physics is really the radius of the electron orbit on the hydrogen atom, at the center of the electron orbit of the hydrogen atom, and it's a given. It's 0.05 angstrom, 0.05 nanometers. This is a permittivity because this wavelength involves some Coulombic interaction between the electron and the core, and it involves the electron mass because it involves an orbital motion. Okay, so that's one thing. Now, in a crystal, this orbital motion gets expanded because the mass is replaced by the effective mass. And this Coulombic interaction is also modified because the dielectric constant is different in the medium. So the Bohr radius, effective Bohr radius in the medium is the Bohr radius of the hydrogen atom, and then divided by the effective mass over the free electron mass and multiplied by the dielectric constant over the permittivity of vacuum. The second concept is Sommer-Fermi screening. So imagine that you have an impurity here, positively charged impurity, and imagine the rest of your solid is treated as a uniform background. So you have one impurity here that has a deeper potential well than all the others. So let's then write that screened potential around this impurity as R over some characteristic length, which will be the Sommer-Fermi screening length, and here we find the dielectric constant again. R, that is just the spatial distribution of this potential. Okay, so in a metal in which you have Fermi-Dirac distribution functions, this impurity will locally perturb the charge distribution, and it might eventually trap an electron. It could. Okay, so we have then calculate RTF here, the length scale over which this happens. And Simon does that by using a Poisson equation around this perturbing potential. And here is the length over which that perturbation happens. It's the dielectric constant permittivity of vacuum. And here you have the density of states at the Fermi energy, which of course describes the amount of electrons you have here. In the Fermi liquid, we can displace this density of states by what it is for a Fermi liquid with a parabolic dispersion, and we end up having RTF as A star B over KF. Okay. So we have all the notions that you're going to need to establish the limits for diffusive transport. Diffusive transport stops being applicable when one of these two criteria is not met. There are two criteria. One is the Anderson limit, which is based on quantum mechanics, often called the Joffrey-Regal limit. I don't know, depends on whether you're Russian, Joffrey-Regal, or American, Phil Anderson. So it looks very intuitive, but actually it's not. It tells you, for electrons to develop a band structure, the electron wave vector must exceed the mean free path. So this is Kf times L larger than 1. In other words, you cannot describe an electron by the dispersions that we have if the electron hits something within one Brillouin or within one Kf vector. So this is a relation between mean free path and really the Bragg wavelength. You have to have enough space inside the periodic lattice to develop your band structure. If you hit something before you're at the Fermi level, you cannot describe the problem with that Fermi level. From this, we then will derive the concept of minimum metallic conductivity, which is simply a macroscopic expression of the Anderson limit. So this tells you that at t equals 0, it is the smallest non-zero value the electrical conductivity can have. So as you change some chemical property of your solid, and you decrease the number of electrons, it will remain a metal, remain a metal, remain a metal at low temperature, and then suddenly it goes insulating. So it's not that you can have metals that continually get decreased electrical conductance. There is a minimum value to this electrical conductance, which, if the bonds are octahedral and you have 6 neighbors, is 610 inverse ohm centimeter divided by the lattice constant in angstrom. So if you have silicon, this is 6, that means 100 ohm centimeter, 0.01 ohm centimeter is the best you can have for conductivity. If you have a sample that has a lower conductivity than that, it's not describable by band structures. Now, that is something that's very, very often overseen or forgotten. Now, you will remember, this is the expression that leads to that. Notice the quantum of conductance, the lattice spacing, and the number of, the coordination number, the number of nearest neighbors. There is a second criterion, which is the criterion for metal insulator transitions, and that is not based on quantum mechanics, but on electrodynamics. So for electrons to conduct freely in your solid, the screened, talking about from the screening wave function of the electrons must overlap each other. And so this then gives you, in 3 dimensions, that the Bohr radius over the carrier concentration, Bohr radius to the cube over the carrier concentration, so this is a pure number, it has to be larger than this quantum number, this number. I don't think we have a 6 there. The formula comes later. Okay, so let's visit the Anderson limit first. So the difference between an insulator and a metal in any arbitrary solid is not just that you have electrons in the conduction band. You also have to have enough electrons that they conduct, and only the delocalized states conduct. So the wave function then is common and goes from unit cell to unit cell. If the wave function of your electron is all stacked up within 1 unit cell, it doesn't conduct. And so that is the conduction, that is the condition that you cannot have collisions that limit your mean free path to something that is smaller than 1 over the wave vector. So if you have this condition is satisfied, you have band conduction. If not, your electrons just go to that unit cell and localize. It's a little bit difficult. It's in Martin Davies there, or it's in Phil Anderson's original paper. Let me derive for you how this leads to the concept of minimum metallic conductivity. So here's your perfect band, and this is your periodic potential, and here's your perfect band. It has a certain width, which we call the bandwidth B. Okay. Now, if you have, instead of a nice periodic potential where all the wells have the same depth, you have some that are much deeper than the others. And let's say this deepest well is at a potential that's V0. Out of line vis-a-vis the periodic one by a quantity V0. Well, if your potentials look like this, randomly distributed, that means that your band is not a nice simple parabola. It means that there are energy states that develops at energies lower than the conduction band minimum. So this basically means that the bands develop something we call a tail. The tail really is electrons that can be in potentials that are deeper than the average. Now, if they're not so deep that they can still jump to the next potential, we still have conduction. But if they are so deep that they get stuck here, then you have no conduction. So you can see that in these band edges, some conduct if they're close enough to the band edge, in these tails. Some states conduct if they're close enough to the band edge, but other states don't. So how do we get to those that conduct and those that don't? Of course, there's a critical energy whereby these electrons get pinned. So if they get stuck in a well that's so deep that they're below this critical energy value, they will get localized. If they're above that, they can just move on. Okay, so let's derive that. So here are these bands, and this tail is here. This is a density of states as a function of energy. So I don't need a band picture. I can do this argument with the density of states argument only. And somewhere here is the critical energy, and the electron falls below that. These are states in the tail that don't conduct. And these can be states also in the tail, but they do conduct. So conductivity is 0 below, conductivity is non-zero above. That's the mobility edge. If I were to plot this instead of in density of states as a function, conductivity as function of energy, I would have a sharp fall in conductivity. This, by the way, is the Mott conductivity of the transmission function, as we learned before. Now, if your electrochemical potential is below, if your electrochemical potential falls here, you can still conduct, but only by hopping from impurity to impurity. If you're above, you have good old band conduction like we described before. So the question is calculating this critical conductivity, this critical transmission coefficient. Well, I'm not going to go through the derivation. It's all in Mott and Davies, but I will explain to you what the critical components are of the derivation. All right, so it's clear that the distance over which you have to move an electron out of this deepest V0 well is going to have something to do with interatomic distance, A. So we're clear this sigma min is going to be proportional to 1 over A. The second thing we need is a quantum of conductance. If we were to just look at the transmission function, we would take this away, but if we look at the conductance, we have to multiply by the quantum of conductance. Now, what matters also, of course, is this bandwidth that I showed before. In other words, here, you have the width of the band, which is a function of the shallowness of the potential wells there. So if this bandwidth is very large, you will have a relatively easy way of conducting. So we're going to have the bandwidth in the numerator. Now, if the deepest potential well is very deep, you're going to have lower conductance, so we're going to put this in the denominator. We have 1 over A h squared here. The other thing that matters is how many chances you have to get out of that deep well. Can you go in 6 directions because you have 6 nearest neighbors, only 4 directions because you have only 4 nearest neighbors. So you can see that the coordination number also matters, and it comes here. Okay, so that then is the form of the formula. It's of course derived rigorously there, but you went through all the ingredients that go in this. Okay, so this is in conductance. Now, what's the best you can do? Well, there is a limit. This width over potential depth is 2 when Kf over L is 1. So this is the best you can do. That's also derived. So we replace this by 2. 2 and 2 cancels, and that gives you the formula for sigma min. Pi squared over z, e squared over h, 1 over a. That's the formula we had before. So this z is 6 in the example that I gave here. That's the z. Okay. There we go. That's minimum conductance. And this, of course, with Z6 is 610 inverse ohm centimeter divided by that in angstrom. It's a classic test that you have to do for all your samples. Take a sample and measure the amount of ohms and convert that to this value. If you are below that value, if your resistance is above that value, and typically for a sample it will be on the order of an ohm centimeter, then you can't apply the formulas that we derive for diffuse transport, such as the Hall coefficients and whatnot. It just doesn't apply. All right. Now let's look at the other criterion. The Mott criterion for the metal insulator transition. So let's consider a degenerately doped semiconductor, because that's the easiest thing to work with. And you fill your bands up to a value, mu naught, that's above the edge of the conduction band, just as an example. Now, let's say that you don't fill it very deep. You fill it, say, 1 MeV above a gap above the band edge, and then you have a 3 EV level below. Okay, so now look at your sample, your entire sample in real space. And of course, there are going to be potential wells in that sample. And then from time to time, you have a potential well. That's again a value V naught, deeper than all the others. Well, as your electron moves over these potential wells, when it sees one of these depths, of course, the gap goes up because the sample is more ionic here. And so, but your Fermi energy, electrochemical potential has to be the same everywhere. That's thermodynamic equilibrium, that's a law. So it's this bottom that moves up and down in the sample as you walk over the sample in real space. So there's this distance here. Mu naught is here, at the bottom of the conduction band moves in physical space. And from time to time, the bottom of the conduction band goes above the electrochemical potential. So in other words, here, the sample will not conduct. This will be a local insulator. But of course, you can go around it if you're in 3D, but not if you're in 1D, because there's only one location to go. So if you were in a one-dimensional system, a quantum wire, and you have one of these things, you can see that at 0 Kelvin, this will stop conduction, just completely. If you're in 2D, well, it's an island where you can't conduct, but you can conduct around it. If you're in 3D, it's a ball, you can't conduct, but you can get around it. So now the condition that you can be blocked depends on the ratio between the Bohr radius and the screening length. So let me explain this. If the effective Bohr radius is larger than the screening length around the island, so the physical dimension of this island is actually the Thomas Fermi screening length. If your Bohr radius is larger than that screening length, the electron can simply wave over it. But if it's not, the electron will be stuck by this unit. In 1D is a very simple argument. In 1D, you have this location on the sample where you can't go. You have then the spatial extent of your wave function, and if that wave function can be larger than this little island, than this little barrier, it will just go through it, it will tunnel through it. But if it's smaller, it will be blocked. That's this condition. In 3D, it's a percolation problem, a little bit more complicated. So let's do that here. If you have your metal, and you have these impurities that are deep, but you have a large Bohr radius, so that they overlap between the impurities, well, the conduction goes through. If the Bohr radius is on the order of the screening length, then you can have local percolation paths, but if it's too large, sample will stop conducting. So at the threshold, you have a percolation problem. Above the threshold, you have a nice metal. Below the threshold, you have an insulator. And let's write the threshold. Now we substitute the values for RTF that we had before. RTF is related to KF, and therefore it's related to the carrier concentration. So we write this condition as A times the number of electrons in a 3D system. So this because of the KF term in here. And that becomes 1/4 of pi over 3 to the 1/3, which is 0.25. That is the condition for band conduction. If you have this, you will have freeze out at low temperature. So basically, if you have a percolation problem and you're at high temperature, you can still get thermally excited across these barriers. At high temperature, you can get KT above and you can go above it. But at low temperature, this is a total barrier. And unless you can tunnel through it, which is this condition, you are not going to have any conduction at all. So your sample will freeze out. A little bit more complicated in 3D, but here it is. This means that at low temperature, you will have freeze out. You cannot tunnel from impurity to impurity. Okay, so now we take this condition And we say, well, what is the carrier concentration at which we will have freeze out? Well, that's the critical carrier concentration, and therefore the condition for band conduction is that you have a carrier concentration higher than 0.016 over your Bohr radius to the third power. That you cannot freeze out a sample that has more carriers than that, but you cannot have low temperature conduction in a sample that has less carriers than that. This is, for example, the problem with topological insulators. If you take bismuth selenide as a topological insulator, bismuth selenide has a very, very large Bohr radius, which means that your critical freeze-out concentration has to be 10 to the 12 electrons per cubic centimeter, which you can almost never get. So yes, you can have very nice surface states, but you can't make the bulk insulating because you can't make the Mott criteria. There is another way. If you substitute the mean free path as the relaxation time and the Fermi velocity, which is related to the Fermi wave vector, which is related to the Thomas Fermi screening length, you can rewrite this condition, and you have mu is L over Kf, and you have a relation between L and Kf, which is actually the other condition. So let me show you how this all falls for real semiconductors. So here, for example, is the mobility of semiconductors as a function of carrier concentration. And we're going to be working at low temperature. And so you can take germanium. Where's germanium? Germanium's here. You can take germanium and dope it progressively less and less and less and less. And then at this n-crit, which is here, the conduction falls, the mobility falls. Notice that this condition, which is this one, this is the Joffe-Regel limit, Kf times mean free path is 1. These are two different conditions. It turns out they very often coincide more or less, but not quite. Here is silicon. You have you dope silicon less and less and less, and you can go to low temperature. And low temperature here, you will freeze out your silicon if you have your carrier concentration at 1017 or below. If you have your carrier, 31018. If you have your carrier concentration at 1019, it will never freeze out. Germanium at 1017 will never freeze out, but silicon will freeze out here, and you get the Joffe-Regel limit here. Now, some are very, very interesting. Strontium titanate never meets this, and the reason is the dielectric constant is very high and the Bohr radius is very high. Lead telluride never meets that because it has both the small mass and the high dielectric constant. So to freeze that lead telluride out, you'd have to have 1010 carriers, which you can't get, and that's 1012 is pretty much the same problem in bismuth selenide. But in contrast, silicon and germanium are fairly easy to freeze out. Okay, so typically you cannot freeze out narrow gap semiconductors like bismuth selenide. So the quest for topological insulators in bismuth selenide is extraordinarily difficult. The materials look easy, but it's extremely difficult. I have a paper on that. Now, obviously this argument is easy to understand in one dimensions. It's also clear that it depends on the dimensionality of the problem. So you will have better freeze out in a quantum wire than you will have in a 3D solid. And there is a very nice analogy in Abrikosov's book, because we have this criterion for the bottom of the conduction band, and we have your electrochemical potential. In 1D, it's very easy. If your electrochemical potential is above the bottom of the conduction band, you always pass. If you have one barrier, you will get reflected unless you have tunneling, but that's a condition we went through. So it fails. Now, if you have two dimensions, it's like having an airplane fly over a mountain range. So in 2 dimensions, your airplane doesn't get stuck at the first mountain it finds. That's higher than its altitude. It actually can fly around, and it gets stuck only if the mountain passes are higher than the altitude at which you are. So at high altitude, you fly over the tops, and everything's fine. At very low altitude, the first pass you encounter will stop conduction, and if the airplane flies in between the height of the mountain and the height of the passes, it can fly around the mountains. In 3D, it's the same thing. It's just a little bit more extensive, and that's what we did before. That's it for today. Thank you.